Here we are discussing about quantum mechanics, right? In quantum mechanics, a physical quantity is represented as some operator A, or it is called an observable. I tell you some examples. Examples are position operator and the momentum operator. In classical mechanics, these are position and momentum, but in quantum mechanics, these are position operator and the momentum operator. So the physical quantity is represented by some operator form. That is, it is called an observable. And what is this uncertainty? We discussed the idea of uncertainty also. Uncertainty in mathematical way, it is RMS deviation, that is root mean square deviation of a physical quantity from its mean, that is its mean value, average value. That is in mathematical form, delta A equal to root of expectation value of A square minus expectation value of A all square. And I told you the reason behind the uncertainty in quantum mechanics. In quantum mechanics, if a particle is moving with a certain velocity, then it becomes a wave packet, right? So the particle can be anywhere in between the wave packet. Okay, it can be here or anywhere. That is, the particle is spreaded over this delta x. So there is a uncertainty in its position. That is why it is called delta x, uncertainty in position. We can say the exact position of the particle. Now, what is the uncertainty principle? Let A and B are two operators or two physical quantities, and if you are trying to measure them simultaneously, then what will happen? Then there will be an uncertainty, that is, in general, delta A, delta B is greater than or equal to commutator A, B, expectation value by 2i. So this is the general formula. And there is a condition. This general formula is valid only for Gaussian wave function. That is, the wave function looks like psi proportional to e raised to minus ax square. We can apply this general uncertainty principle only for those wave function which have a Gaussian profile. Okay, this one is a very important formula. Please remember this. Okay, here we can consider two cases. The first case, if commutator AB is equal to 0, then what do we obtain? We obtain delta A, delta B is equal to 0. That is, uncertainty is 0. That means we can measure them accurately. Right? Because uncertainty is 0. That means we can measure them accurately. Now, second condition. Suppose A operator is operating on a state psi, we obtain A psi, and a B operator is operating on psi, we obtain B psi. Now, we can find commutator A, B. That is equal to, we know What is this one? That is AB minus BA psi. We can expand this, that is AB psi minus BA psi. I told you how this operator will operate on state. First, this A operator will operate on psi, then B operator will operate on psi. Here also, first B operator will operate on psi, then A operator will operate on that quantity. That is, A is there. Okay, so when B operator operates on psi, we will get B psi, right? Minus B. Now A operator is operating on psi, so we will get A psi. Here I can take this constant outside, that is B A operator on psi minus A B operator psi. Now we can operate this A operator on psi and B operator on psi. So what we will obtain, that is equal to B into, when A operator operates on psi, we will get A psi minus A, when B operator operates on psi, we will get B psi. That is equal to BA minus AB into psi. And if commutator AB is equal to 0, that means BA minus AB is equal to 0. What is its meaning? That is, measurement of A on psi never affect the measurement of B on psi. These measurements are independent. One measurement never affect the other measurement. Okay, that means we can measure them simultaneously, because one of the measurement never affect the other measurement. Therefore, we can measure them simultaneously. And if a commutator of two operators A and B is equal to 0, then these physical quantities said to be compatible. That is, if commutator of two operators A and B is 0, then we can say the physical quantity A is compatible with the physical quantity B. Now let us summarize these ideas. First one is, if we want to find out the uncertainty in a single physical quantity, that is delta A. Okay, then that will be equal to root of expectation value of A square minus expectation value of A all square. Okay, and if we want to find out the uncertainty in product of two physical quantities, that is delta A delta B, then the equation is delta A delta B greater than or equal to expectation value of commutator A B by 2I. Please remember these two equations. These are very, very important. Example problem. A wave function is given, that is psi of x is equal to A e raised to minus A mod x. And the question is to find out delta x and delta p. That is uncertainty in position and uncertainty in momentum. So first we have to solve delta x. So how we can? And we know delta x is equal to root of expectation value of x square minus expectation value of x all square. So we have to find out expectation value of x and expectation value of x square. But before evaluating this x and x square, we have to normalize this wave function. Why? Because we have to find out the value of a. To find out this value of a, we have to do the normalization. That is, the formal way is the normalization condition is integral minus infinity to infinity mod psi square dx should be equal to 1. Okay, so you have to substitute this value of psi of x here and evaluate this. That is integral minus infinity to infinity mod psi square is a square raised to minus 2a mod x dx, and equate this obtained value to 1. Then you can find out the a value. But earlier I told you a trick. What is the trick? See, this is a function psi of x is equal to a into e raised to minus a modulus of x. If it is some modulus of x, then this a value will be equal to root of coefficient of mod x. So here by this trick, the value of a will be equal to root a. So the normalized wave function will be equal to root a e raised to minus a mod x. So if you are remembering this trick, then very easily we can find out the normalized wave function. Now we have to evaluate delta x. Now first we have to evaluate expectation value of x. What is expectation value of x? This is nothing but bra psi x ket psi. Okay, that is minus infinity to infinity bra psi, that is root a e raised to minus a mod x into ket psi, that is root a e raised to minus a mod x into dx. That is expectation value of x is equal to minus infinity to infinity, here root a into root a, so I can take that constant outside, into x into e raised to minus 2a mod x into dx. Here you can see x is a odd function and e raised to minus 2a mod x is a even function. That is, the entire function is odd function into even function, that is odd. That is, this entire function is an odd function. So if you are integrating an odd function from minus infinity to plus infinity, its value will be equal to 0. Therefore, this is equal to 0. Maybe you have this doubt. Why this integral from minus infinity to plus infinity of a odd function is equal to 0? I tell you. Suppose this is a function. This is an odd function. I am going to plot an odd function. That is, this is odd function. In the negative x-axis, it is negative, and in the positive x-axis, it is in the positive. So this is a odd function. Now I am going to integrate this function. So this is minus infinity and this is plus infinity. Okay. Now I am going to integrate this function from minus infinity to plus infinity. That odd function with respect to dx. So I can write this function as 2 integral, that is 1 from minus infinity to 0 dx, plus second is from 0 to infinity dx. Okay, this odd means function, odd function. So when we are integrating this portion, that is what I get, the area under the curve. That is what integration, right? So I will get this much, this area, right? This area is in the negative axis, so this will be some negative area, some negative q. Okay, so this is equal to minus q, plus now we have to integrate from 0 to plus infinity this time. Okay, so when we are integrating, we will get this area. That is, integral is nothing but area under the curve. So here this is in the positive axis. If this is y, then this is in the positive axis, then we will get an area plus q. Okay, plus q. That is, adding these two is equal to 0. That is why I told you integral of a odd function from minus infinity to plus infinity is 0. Because in the negative axis it will be have a negative value, and the positive axis it will have a positive value. So these two areas will cancels each other. So we got expectation value of x is equal to 0. Now we have to evaluate expectation value of x square, that is equal to, here also this is nothing but brass psi x square get psi. Okay, that is we get minus infinity to infinity. When substituting this psi value, you will get a into e raised to minus 2a mod x into x square. Okay, here x square is even function, and this one is also even function. So product of two even function is also even function. So this is not equal to 0. That is, expectation value of x square is equal to a into integral minus infinity to infinity x square e raised to minus 2a mod x into dx. Now I am going to rewrite this as expectation value of x square is equal to a into integral minus infinity to 0 x square e raised to minus 2a into mod x. Mod x in the negative region will be negative x. So this will be plus 2ax dx plus the remaining integral is from 0 to infinity x square raised to minus 2a. Value of mod x in the positive region is plus x, that is x dx. When you are evaluating, both of this integral will give the same value. Therefore, I can rewrite as expectation value of x square is equal to 2a integral 0 to infinity x square raised to minus 2ax dx. And you can directly solve this integral, or earlier I told you a trick, that is, if there is a function that is from 0 to infinity and it is x raised to n raised to minus x dx. If it is in this form, then its answer will be n factorial by a raised to n plus 1. So we can use this trick here. So we can find out the answer directly. That is, expectation value of x square will be equal to 2a into, here n value is equal to 2, right? And a is equal to 2a. So substitute these values here. So what will we get? Into n factorial is 2 factorial by a is 2a raised to n plus 1, that is 3. So we get expectation value of x square is equal to 1 by 2a square. So we got the expectation value of x and the x square. Now we can find out delta x. That is, delta x equal to root of x square minus expectation of x square. That is, delta x equal to root of, we got the x square value. What is that? That is 1 by 2a square minus, we got expectation value of x, that is 0. That is, delta x is equal to root of 1 by 2a square, or delta x equal to 1 by root 2a. Okay, so this is the uncertainty in position. If the wave function is psi of x equal to root a raised to minus a mod x, then this will be the uncertainty in measuring its position. That is, this corresponds to a particle. Okay, this wave function corresponds to a particle, and if you are measuring its uncertainty in position, then we will get this value. Okay. Now we have to find out uncertainty in momentum. Okay, the wave function is same, that is psi is equal to root a raised to minus a mod x. So how we can find out delta px? That is, delta px equal to root of px square expectation value minus px expectation value square. So first we have to evaluate expectation value of px. That is, expectation value of px is bra psi px get psi. That is equal to integral minus infinity to plus infinity. Bra psi is equal to root a e raised to minus a mod x into px, where px is px operator, right, into psi. What is psi? Again, root a e raised to minus a mod x dx. And we know the momentum operator px is equal to minus I h cross dou by dou x. So we have to substitute those value. That is, expectation value of px is equal to minus infinity to infinity. Here root a into root a, so it's a into e raised to minus a mod x. Px is equal to into minus I h cross dou by dou x into e raised to minus a mod x dx. So here I can take the constant terms outside, that is minus I h cross a integral minus infinity to infinity e raised to minus a mod x into dou by dou x of e raised to minus a mod x dx. So first you have to evaluate this term, that is dou by dou x of e raised to minus a mod x. So how we can do that? First you have to separate this integral into two. That is, one is from minus infinity to 0 plus another is from 0 to infinity. Okay, then you can do this partial differential, then do the integration. So finally you will get the answer for expectation value of px. See, this job is a very difficult one. So here I'm not going to solve this integrals. I'm going to use a trick. What is the trick? Trick is, it is already discussed with you. That is, we know in classical mechanics px equal to mass into velocity, right? That is, px equal to m into velocity is nothing but dx by dt. So I'm going to take expectation value of momentum, that is average value of momentum, that is equal to average value of m into average value of dx by dt. Here m is a constant value, so its average value will be m itself. Therefore, expectation value of px will be equal to m into d by dt of expectation value of x. And here in the early solution we got the value of expectation value of x, that is equal to 0. Therefore, definitely the expectation value of px will be equal to 0. So I got the value of expectation value of px. But to find out delta px, that is root of px square minus expectation value of px or square. We got the second term. Now we have to evaluate the first term, that is expectation value of px square. Okay, I'm giving this as a work for you. Please try to find out the expectation value of px square. There is some integrations only, so you please try to do this expectation value of px square, and finally you will find out what is the value of delta px. Okay. Equation of motion. In classical mechanics, we are very much familiar with the equation of motion. That is Newton's equation of motion. What is this Newton's equation of motion? That is, if there is a particle of certain mass m and it is moving with a certain velocity v and have a certain acceleration a, then f is equal to ma. That is the Newton's equation of motion, right? And we know what is A? A is nothing but dv by dt. That is rate of change of velocity. Okay, that is F is equal to m into dv by dt. Here I am going to rearrange this equation. That is dv by dt is equal to F by m. That is equation of motion is nothing but time derivative of velocity. See, velocity is a physical quantity. Okay, so the equation of motion is nothing but its time derivative. Okay, that is dv by dt. That is what I am going to tell you is equation of motion is rate of change of physical quantity with respect to time. Okay, that is why dv by dt is equal to F by m is a equation of motion, a classical equation of motion. But now we are discussing a quantum mechanics. So in quantum mechanics also I want to find out an equation of motion. So in quantum mechanics we know a physical quantity. It is called an observable and it is represented by as an operator, a cap. Okay, and the measurement of this value, measure of a physical quantity is expectation value of A, that is bra psi A psi. Now I want to find out equation of motion. In classical mechanics, I told you equation of motion is nothing but time derivative of a physical quantity. That is, equation of motion in quantum mechanics will be d by dt of A. That is d by dt of what is expectation value of A? That is bra psi A get psi. So this is equation of motion in quantum mechanics. Now we can elaborate this equation and find out some simplest form, that is d by dt of bra psi A get psi is the equation of motion in quantum mechanics, and here I can expand this derivative. How? That is dou psi by dou t A get psi plus bra psi dou A by dou t get psi plus bra psi A get dou psi by dou t. Here I want to substitute for bra dou psi by dou t and get dou psi by dou t. So I want to find out these values. Okay, so to find out these values I am going to use Schrodinger equation. What is Schrodinger equation? That is time dependent Schrodinger equation. That is I h cross dou psi by dou t is equal to h psi. Here I am using this Dirac notations, that is get dou psi by dou t and the get psi. So what I want to find out? Dou psi by dou t. Okay, so I am rearranging this equation. I am taking this I h cross to RHS of this equation. Therefore, I will get dou psi by dou t is equal to 1 by I h cross h get psi. Okay, so I got the value of this tape. Now I want to find out this one, bra dou psi by dou t. So what I am going to do is I am going to take conjugate of Schrodinger equation, that is minus I h cross bra dou psi by dou t is equal to bra psi h. Okay, this is nothing but conjugate of Schrodinger equation. Complex conjugate of Schrodinger equation. Okay, now I want to find out this term only, so I am taking this to RHS. That is, I will get bra dou psi by dou t is equal to 1 by minus I h cross bra psi h. Okay. Now I can substitute these two terms in the above expression. That is d by dt of bra psi a get psi is equal to bra dou psi by dou t. That is this term. That is minus 1 by I h cross into bra psi h. The remaining is a psi plus bra psi dou a by dou t get psi plus bra psi a. Now we have to substitute dou psi by dou t, that is 1 by I h cross. I am taking this 1 by I h cross here into h get psi. Okay, see, these two terms are similar terms, so I can rewrite it in a, that is d by dt of bra psi a get psi, that is equal to 1 by I h cross into bra psi a h minus h a get psi plus bra psi dou a by dou t get psi. Here this is nothing but commutator a h. Okay, so d by dt bra psi a get psi is equal to 1 by I h cross into expectation value of commutator a h plus bra psi dou a by dou t get psi. That is, by using Dirac notations, we can rewrite this as d by dt of expectation value of a is equal to 1 by I h cross expectation value of commutator a h plus expectation value of dou a by dou t. This is called Heisenberg equation of motion. This is the equation of motion in quantum mechanics, similar to equation of motion in classical mechanics, that is F is equal to ma. Now let us consider some special cases of Heisenberg equation of motion. So the first case is the commutator AH. Commutator of an operator with a Hamiltonian is equal to 0. That means A commutes with the H. That is, you can measure both the energy and this A operator of a particle simultaneously. And dou A by dou T, partial derivative of operator A is also equal to 0. And other condition is 1 by I h cross expectation value of commutator A h is equal to minus dou A by dou T. For both of these cases, we will get d by dt of expectation value of A is equal to 0. Right? That means A is constant of motion. Or A is integral of motion. Or we can say A is conserved. That is, if d by dt of expectation value of A is equal to 0, then we can say A is a constant of motion, or it is an integral of motion, or it is a conserved quantity. And for d by dt of expectation value of A equal to 0, there will be two conditions. One is independently the commutator AH will be 0 and dou A by dou T equal to 0. Or 1 by IH gross expectation value of commutator AH will be equal to negative value of expectation value of dou A by dou T. Okay. For these two conditions, we can say A is a constant of motion. Ehrenfest theorem. What is Ehrenfest theorem? Ehrenfest theorem connects quantum mechanics with the classical mechanics and vice versa. Okay. So before that, you have to know what is the Heisenberg equation of motion. What is it? The Heisenberg equation of motion is d by dt of A is equal to 1 by IH gross expectation value of commutator A with the Hamiltonian plus expectation value of dou A by dou T. And in quantum mechanics, what is this Hamiltonian operator? The Hamiltonian operator is nothing but energy operator. We know in classical mechanics, energy E is equal to kinetic energy plus potential energy. That is, what is kinetic energy? That is P square by 2m plus potential energy is V of R. Okay, this is the energy equation in a classical mechanics. So similarly, in quantum mechanics, this become operators, that is P cap square by 2m plus V of R. Now, first we have to find out d by dt of expectation value of R, that is position operator, right? That is equal to, we can use the Heisenberg equation of motion, that is 1 by IH cross expectation value of commutator A, here A is R operator, into H. What is this H here? H is P cap square by 2m plus V of R plus dou A by dou T, that is dou, here it is dou R by dou T. Here you can see this R doesn't have any explicit time dependence, therefore this is equal to 0. That is equal to, we got 1 by IH cross expectation value of, here we can expand this commutator, that is commutator R cap P square by 2m plus commutator R cap V of R. Here this is R and is a function of R. So when we are learning the commutator operator, we know this is equal to 0. Okay, that is, this is equal to only 1 by IH cross, and here I am taking the constant from inside the commutator operator, that is into 1 by 2m into expectation value of commutator R P square. And I told you how we can solve this commutator, that is commutator R P square is equal to commutator Rp into derivative of P square. Okay, that is, this is equal to commutator Rp, that is position and momentum. So this is IH cross into derivative of P square is 2p. Okay, so we can substitute this value here, that is equal to d by dt of expectation value of R is equal to 1 by IH cross into 1 by 2m into expectation value of I h cross into 2p. So here we can cancel this IH cross and IH cross and this 2 and 2. So finally we will get d by dt of expectation value of R is equal to expectation value of P by M. See, this is similar to classical mechanics, that is dr by dt is equal to, that is, what is dr by dt? That is nothing but velocity, right? And what is P by M in classical mechanics? That is, P is mass into velocity by mass. So mm will cancels and we get velocity. Okay, so d by dt of expectation value of R is equal to expectation value of P by M is similar to the expression for velocity in classical mechanics. That is why I told you the Ehrenfest theorem relate the quantum mechanics and the classical mechanics. Now let us consider the second one, that is d by dt of expectation value of P. That is, we can use the Heisenberg equation of motion, that is equal to 1 by I h cross expectation value of P with the Hamiltonian plus dou P by dou t, expectation value of dou P by dou t. That is, we have to substitute this Hamiltonian here, that is 1 by I h cross expectation value of P, and Hamiltonian is P square by 2m plus V of R plus dou P by dou t. And here also the momentum P doesn't have an explicit time dependence, so this will be equal to 0. And the remaining is, this is equal to 1 by I h cross expectation value of, we can separate this commutator operator, that is, one is P cap comma P square by 2m plus P cap comma V of R. See, this definitely will be equal to 0 because P and P. Here P and V. Now what is this commutator of P comma V of R? We know this will be equal to commutator of P comma R. Then we have to take the derivative, that is V of R derivative. Okay, so here momentum is first, then position. Their position is interchanged, therefore it will be minus I h cross and derivative of V of R, that is dou V of R by dou R. Therefore we will get d by dt of expectation value of P is equal to 1 by I h cross into expectation value of minus I h cross dou V of R by dou R. So here we can cancel this I h cross and I h cross and we will get d by dt of expectation value of P is equal to minus expectation value of dou V of R by dou R. This is the quantum mechanical expression. Okay, and I told you the Ehrenfest theorem relate classical mechanics and quantum mechanics. So in classical mechanics, what is this value of d by dt of P? That is equal to d by dt of mv, that is ma, that is equal to force, right? And what is this negative gradient of dou V of R by dou R? I told you in classical mechanics, this is nothing but force. Force is negative gradient of potential. Now we can summarize the Ehrenfest theorem. That is, we got two important formulas. First one is d by dt of expectation value of R is equal to expectation value of P by M. That is, this is equation for velocity. And second one is d by dt of expectation value of P is equal to minus expectation value of dou V of R by dou R. This is for force. Now let us discuss example problems. First example problem, Hamiltonian is given, that is h is equal to px square by 2m. And this is for a free particle. For a free particle, the potential will be equal to 0. Okay, that is why there is no potential time. And the question is to find d by dt of expectation value of x and d by dt of expectation value of p and d by dt of expectation value of h. That is, we have to find out the equation of motion for x, equation of motion for p and equation of motion for h. That is the question. So first you have to find out d by dt of x, that is equation of motion for x, that is equal to, we can use the Heisenberg equation of motion, that is 1 by IH cross expectation value of x cap h plus dou x by dou t. So here you can substitute these values of Hamiltonian here, that is equal to 1 by IH cross commutator x cap, h is p x square by 2m plus dou x by dou t. Here dou x by dou t is equal to 0. That is, there is no explicit time dependence on x. Okay, so we can solve this commutator. So we will get this is equal to 1 by IH cross 1 by 2m into commutator of x p into derivative of px square. Okay, that is, we get this is equal to 1 by IH cross into 1 by 2m expectation xpx is I h cross into derivative of px square is 2px. That is, we can cancel this 2 and 2 and IH cross and IH cross. So finally we will get the answer, d by dt of expectation value of x is equal to expectation value of px by m. So here you can directly use the Ehrenfest theorem also. See, this is the solution of Ehrenfest theorem, right? So if in a question is there, then you can directly use the Ehrenfest theorem also. So you can directly find out the answer. Second one, that is d by dt of expectation value of px. To find out the equation of motion of px, you can use Heisenberg equation of motion, that is 1 by IH cross expectation value of px h plus dou px by dou t. This is Heisenberg equation of motion. By solving Heisenberg equation of motion, you can find out the value, or you can directly use Ehrenfest theorem. What is Ehrenfest theorem? In Ehrenfest theorem, d by dt of expectation px is equal to minus expectation value of dou v of x by dou x. Here, what is the v of x value? That is, given Hamiltonian is equal to px square by 2m, and it is for a free particle. That is, there is no potential time. That is, v of x here is equal to 0. Therefore, we get the equation directly. So we get the solution directly from the Ehrenfest theorem. That is, d by dt of px is equal to 0. or you can solve this Heisenberg equation of motion, but it take time. So use Heisenberg. So please use Ehrenfest theorem so you can easily solve. Now third one, that is d by dt of expectation value of h. That is, we have to find out equation of motion corresponds to Hamiltonian. That is, here there is no Ehrenfest theorem. We have to use Heisenberg equation of motion. That is 1 by IH cross expectation value of h plus dou h by dou t. See, the given Hamiltonian is this one. Okay, so there is no explicit time dependence. Therefore, dou h by dou t is equal to 0. And we know the commutator of same operator also will be equal to 0. So, d by dt of h is equal to 0. Now, let us consider another example. In this example, Hamiltonian is equal to px square by 2m plus half k x square plus a x cube. Here also the question is to find out d by dt of x, d by dt of px and d by dt of Hamiltonian. So we have to find out the equation of motion of x, px and h. Here completely I am going to use Ehrenfest theorem. You can use Heisenberg equation of motion, but it takes time. So I am using only the Ehrenfest theorem to solve this equation. So first question is d by dt of expectation x. We know by Ehrenfest theorem this is equal to expectation px by m. And second one, d by dt of expectation px. And by using Ehrenfest theorem, this is dou v of x by dou x. Here, what is this dou v of x? See, this is the potential time and this is a function of x. So we have to evaluate, that is minus dou by dou x into v of x, that is half k x square plus a x cube. That is equal to minus into, we can take the derivative of this function, that is we get k x plus 3 a square. So we got d by dt of expectation px. Third one, d by dt of expectation h. That is equal to, here we cannot use Ehrenfest theorem, we have to use Heisenberg equation of motion, that is 1 by IH cross expectation value of h plus expectation value of dou h by dou t. Here in this Hamiltonian we can see time t time. Okay, that means there is no explicit time dependence on this Hamiltonian. So this is equal to 0. And we know commutator of same operator will be equal to 0. That is d by dt of h is equal to 0. One more example. Here the Hamiltonian is equal to px square by 2m plus half kx square plus q e x cap cos omega t. Here also the question is find out d by dt of x, d by dt of px and d by dt of h. So first one, d by dt of x. Here I am using only Ehrenfest theorem, that is equal to expectation px by m. Second one, d by dt of expectation value of px. Here also I am using only the Ehrenfest theorem, but you can solve this problem by using Heisenberg equation of motion also, that is minus dou v of x by dou x. Here see, this is the potential time, that is v of x. That is, this is equal to minus dou by dou x of half k x square plus q e x cos omega t. That is minus, we have to take a partial derivative of these terms with respect to x. So we'll get kx plus q e cos omega t. So we got the answer. The next one is d by dt of h. That is equal to, here we have to use Heisenberg equation of motion. There is no Ehrenfest theorem for finding this value. That is equal to 1 by I h cross expectation h plus expectation dou h by dou t. Here you know commutator with the same operator will be equal to 0, but here this Hamiltonian is a function of time. That is, there is a time coordinate in the Hamiltonian. That is, this is equal to, that is d by dt of h is equal to dou by dou t of Hamiltonian, that is px square by 2m plus half k x square plus q e x cap cos omega t. So when we are taking dou by dou t of this term and this term, it will be equal to 0. That is 0 plus dou by dou t of q e x cap cos omega t. That is equal to q e x cap into dou by dou t of cos omega t. That is equal to q e x cap into derivative of cos omega t is minus sin omega t into omega. That is equal to minus q e omega x cap sin omega t.